In this session, we're going to be learning how to wrap a mesh that exists more or less in the XY plane onto a donor object like this low poly vase that I made. We're going to be doing this wrap based on UVs, and it's one of two ways of doing mesh wrapping. This is more suited to doing things which are essentially planar, so things like architectural facades, or you might have fabric, or you might have materials. I know, shoe designers, for example, use interesting textures and things. And to wrap that onto a shoe, quite a complex shape, it can be very much easier to do it in this method. If you're wanting to do the other method, which is essentially a 3D pinning of a mesh to another mesh, that is a different process. And there is an excellent tutorial by Duncan Rudd, which I will link down in the description below. He goes into a lot of detail about the full process and how you go into the vector math and actually work with all of those functions. It's a great tutorial and I definitely recommend you checking it out. This session is much more specifically tailored towards wrapping meshes that essentially exist in the XY space. So without further ado, let's jump in here. I've got a new file open here just with a basic form that we're going to be using. I'll go into that a little bit later. And a couple of collections, one for my form so that I can disable it, and the other one which will be for our wrapped mesh as we work with it. Now, one thing that we're going to need as we get started here is a somewhat flat, or at least for its important axes to be in the X and the Y space. So this might be a building facade, it might be fabric, it might be textures, it might be a clay kind of shape form that you want to wrap around something. Whatever it might be, you just need to have some kind of flat-ish surface. I'm going to be just recreating that facade. I thought I would do it in the video because it's very quick to do and quite a fun process. And you might learn something. So let's create a new node tree here. I'm going to call it facade. Just got this on a plain object here. And I'm going to be using a mesh primitive, mesh grid. Let's view this. And let's use a group input just so we have access to it later to control our vertices. Press N, rename this one to resolution in the X and the Y. Cool. Importantly, the size of this is 1 by 1, so that when we use a transform node, we're going to put this up into the XY space, into the positive XY space by just adding 0.5. Next thing I want to do is increase my resolution to maybe 30, just give myself a little bit of extra topology, and then I'm going to do some manipulation here. So a few steps to do here. Set position, move that over. I'm going to be using a position node, separate XYZ, and I will be then combining XYZ into the position. So right now nothing has changed. If I add a math node, utilities math, onto my X and power it, you can now see that I can sort of deform that mesh one way or other. Now, if I set my exponent as some function of the y-axis, so let's use a map range between 0 and 1, that's the space we're in, put this into my exponent. Now you can see that we're starting here and we're going up. So I will increase my 2 men to maybe 0.1, that's probably fine. I'll set my 2 max to be around 2 maybe. That looks fine. I might also change from linear to smoother step as well, and you get this fun S shape. Now I also want to control my Z axis. Right now there's no way for us to actually see this, it's just a plane to us. So rather than controlling the Z with the original Z, again, going to take a function, this time off the X axis. Let's put this through a float curve, and I will plug this into my Z. Now it's going to go from 0 to 1 across that X axis. I'm also going to add a multiplier on the end of this one, so add a multiply here, and I will add another group input node just to be able to set that height myself. Change the name of this one to height. Rather than this just being linear, let's start and stop in the same place. This is going to make it tileable, or more easily tileable anyway, cleaner tiling. And I will just drag a point up in the middle, set this one to a vector handle maybe, and I'll pull it over to one side and I'll just set this up to a little curve so that we come in from flat, something like that. I'll do the same on the other side, another little curve meeting the bottom, just gives me this nice wave shape. And if you want to have multiple of these curves, you can simply just add more handles. It's that simple. set one of these as well. Maybe I'll add a little bit of a flat spot to that first one. If I increase the resolution, then you can see that we're getting that there. I'll change my height down to maybe 0.2, just make this a little bit less overt. And I will do another one here. Just a little bit lower. There we go, that's quite nice. Okay, so once you've got your profile worked out how you want it, we're going to just quickly knock these together into a grid. Let's just use transform nodes. Transform scale -1 on the X. Join those back together. So there we go, now we've got this nice shape here. Let's do another one where we're transforming -1 in X and Y. And the last one where we're transforming just -1 in Y. If I go back into my viewport overlays, you can see that I've got face orientation. If you want to make sure you have that viewing, you can check face orientation in here. I need to make sure I have flipped just the two transforms that only do it in the one axis. So there we go, and there we go. Nice. This is now our tile. We're going to be instancing on points. This is going to be our instance. I'm going to use a grid. And as cool as this looks, getting this kind of overlay, let's go up to maybe 10. Let's use another group input. And this time I will set my tile count, or tiles X and tiles Y. I will have these separately controlled. Just, you never know what kind of geometry you're going to be working with. I'll set these to 10. And then I want to set my size to be based off this. So we just need to subtract 1 and then multiply by 2. So these tiles are 2 meters by 2 meters, therefore we have a size of 2, and the length that we need is going to be the number of tiles -1. So if you have 1, you don't need any distance because you only have 1 point. If you have 2, you only need 1 of those distances between them. Plug that in like that, and I'm going to duplicate these. That second one there should be a multiply, by the way. Going to go off my tile Y as well into that size. There we go. Nice. Now it's fitting nicely. All looks good. Right now these are all instances with split edges. So let's go in here as well, and we will do a realize and then a merge. You'll notice this merge is taking a little bit of time. So let's make sure we've refined our selection to only be doing boundaries. So let's use an edge neighbors node, taking our face count when it is equal to 1. When an edge only has 1 face next to it, it is a boundary edge. There we go. So now we are doing about 1/3 the computation there. Good stuff. So this is our facade. I'm going to be creating a new node tree for the next part of this tutorial. I'm splitting them up like this just because I'm assuming that facade is probably going to be a separate object for you. Maybe you've modeled it manually. Maybe it's a photo scan, whatever it is. This can be a separate thing. So I'm just dividing it like this. This new node tree I'm going to call wrapper. And now we're interested in our form. So let's have a look at this form. There's nothing particularly special about it, but it's important that we notice the UV map. So if I tab into edit mode, you can see that my UV map, it's not important that it fills the space, but it is important that it has no overlapping islands. You can't have an overlapping island with this setup. It will get confused. It won't know which part it should be sampling the original position from. So important that you have not overlapping UVs. In this case as well, because I want this to go around the cylinder and join, have a clean join on the back, I've made sure that the edges of these are exactly on that 0 and 1 position. If you're working with more complicated geometry, you maybe have more holes, random shapes, random rotations, whatever it might be. We're going to be affording that within this process. As we build this, we're going to have a part where we build a cutter to make sure that we're snipping off parts of the mesh that will not be mapped correctly. So that is going to be dealt with. And then we're also just going to be doing the wrap as well. So let's start off with the wrap here. I'm going to go back to my geometry nodes. On my surface here, I'm going to hide my form, but first let's just bring it into the node tree like this. So I've got this surface, And I want to do some sampling. To get a clear idea of the problem space, let's unwrap this into its UV space. So let's use a set position node. And we will use a named attribute node looking at the UV map. Now, if I just view selected, we can see that this has got a little bit broken up and it's not completely filling the space as we knew the UVs were. This is because the UVs have seams and the object does not. Geometry nodes cannot view the seams. Next best thing we can do is we can just edge split everything. So there we go, let's just do that and we can now see this is our UV layout. This exists in the 0 to 1 space. Our geometry that is going to be mapped to it really does not. This is huge and it will be changing size depending on how many tiles we have and how big it is. So we want a way to make sure that we can map this to the 0 to 1 space. So let's make a tool for this. We're going to be forcing the size. Take a bounding box node on this mesh. This is going to give us information about the size and position. If we now take a transform node as well, and we transform to the minimum, we have gone down in the opposite direction. What we really want to do is invert this. So let's use a vector math, set to scale, and we will be scaling this by -1. So now, importantly, we exist completely in the positive XY quadrant. So it's all in this direction. Now I want to scale this into the XY space, into that 0 to 1 space. If I just use the scale on here, you can see it goes to its original 0th position. This is just because of the order of operations. So all we need to do is add another transform node afterwards that we can use to scale this down to 0. How big is that scale going to be though? It's actually very easy for us to work it out. If we take another vector math node, let's set this one to subtract. We can now subtract the minimum from the maximum. Make sure you cross those noodles. If we then take a separate XYZ and we find which of these X or Y is the largest, let's take the maximum between X and Y. And then I want to plug this into my scale, but if I do this, it's going to get very big. So rather than doing this, we want to do the sort of the reciprocal, the inverse. So divide 1 by that maximum value. And now it exists just in that 0 to 1 space. So the largest axis has been scaled to fit and everything else has been scaled the same amount. So it's a uniform scale based on the largest axis. Now you might not always want this to fit just uniformly scaled. Sometimes you'll want it to be exactly to both the X and the Y 0 to 1 space. Let's have a way to do that as well. So let's add a utility switch node, just to make sure that we have the option. Set this to vector. Going to put our original into the false and output into the true. There we go. And let's switch this to true. So now we're dealing with stretching it across both axes. Now the easy way to do this would be to take our subtract and plug this into our vector here. Make sure that we're plugging it into the bottom of our vector. Set the vector to divide, set the size to be 1, and then plug this into the true. All right. So now it is exactly stretched into X, Y, 0 to 1, but it is also stretched into the Z, which we don't want to have happen. So instead of using this vector this way, we really want to use this original Z, basically from this divide, but essentially do a divide for the X and the Y based on 1 to make them both fit this space. So rather than just using the maximum, scaling everything uniformly, we are going to be taking our X into the bottom. So 1 divided by X, and again, 1 divided by Y. I'm going to use a combine XYZ here to join these together. So I have my X coming through from the X, I have my Y coming through from the Y, and I have my Z coming through from this original divide here. And now you can see that we can now get that stretch all the way across or not all the way across. Let's group these up. This is our force size node group. Control G, F2. This one is going to just call force size. You can always add controls to have this size be set from the outside. I'm just going to leave this as is. So something else that I just need to make sure I'm doing is I'm not scaling the bounding box. I need to be scaling the original geometry. So rather than joining through this bounding box here, we're going to join our geometry through like this. And now you can see we're actually getting our geometry through. Do want to have my group input also controlling this switch here, just to make sure I've got that available to stretch if I need to. Let's rename that to stretch. All right, next part of this. Let's continue on. I'm going to make this uniform anyway, so 14 by 14 tiles seems fine. Now the next part of this is going to be wrapping this tile, which is now in the 0 to 1 space, onto our geometry, because its UVs are also in the 0 to 1 space. This is actually quite a lot easier than you might think. So if I just take a set position, like this, and I'm going to take just another object info node here with my form, and I'm going to sample UV surface. We're sampling a vector because I want to know the position of this surface. The source UV map is going to be the named attribute UV map that is basically the UV map of that surface. And then the sample UV is not a UV at all, it's the actual positions that we've made our input mesh here. So I'm just going to duplicate this because we're going to change it in a minute. Now, let's take these values and we'll just put them onto the positions. Scale this up, and there you go. It's actually not too bad. To make this a little bit smoother, I will add just a subdivision surface onto here. Let's make this maybe 4 levels, that's fine. And you'll notice that this is all going down to 0. So we're going to work out a solution for this a little bit later on. But for now, let's just ignore that. So right now we are wrapping nicely onto the surface. How much more could we need to do? Well, we need to reinflate. Right now, this is completely flat to the surface. Every point is just where it is on the surface. It's not taking into account the original Z-axis of our object. Something that we need in order for us to do that is the normal position at each one of these points. So let's grab another sample UV surface, Control-Shift-D, and instead of plugging through the position, I'm going to be looking for an input normal node into that value. So top one is position, bottom one is normal. In fact, let me just write this. This is the surface position. Bottom one is surface normal. Let's just do something a little bit preemptively here. Let's add a capture attribute up here, set to vector, and I'm going to set this to position. So I'm capturing the position of my unwrapped surface, this original flat surface. The reason I'm doing this is because I need the Z-axis. So let's do a separate XYZ. Let's take the Z-axis. I'm going to put this through a scale node, vector math scale, as the scalar. The normal, the surface normal, is going to be our vector, and this is going to go into our offset of this position node. All right, a little bit better, not perfect. We need to increase this Z amount. So let's add a multiply node, math multiply, and I will just increase this until it looks a bit better. Let's maybe increase our resolution to 20 to make that slightly smoother. All right. This is not bad. You can see we've got some issues here. This is to do with our subdivision. If you change your keep boundaries to something like keep corners, that's going to smooth that out. So our Z-axis stuff is cool and all, but we're not doing it as intelligently as we might be, because right now we're just saying basically make it bigger, right? Manually make it bigger, and it's making it uniform. So at the top it's the same as in the middle as at the bottom. Rather than just doing this uniform height control, let's do this based on the face area scaling. So the reason you might want to do this is on something like this, we have a lot of wider areas in the middle and narrower areas in the top. There's no reason that the height should not be proportional to the size of those areas. Equally, if you're doing something like fabric, when you stretch it, it should get thinner in the middle in general. And therefore, you might want to do some control based on the change in face area. This is very easy for us to set up. Let's take another capture attribute node here, set to float. We are looking for the face area node. And if I just view this, you're going to see these look black. There's really nothing coming through our viewer node. That is because these are such small values. However, if I view the face area on these larger ones, once it's actually been wrapped around, well, now we can actually see something. So there is a clear difference between the face area when it is small and when it is large. The way that we can find the difference between these is quite simple. We simply take a math node set to divide, and we want to divide the current face area, by our captured original face area. There we go. So now if I view this one instead, it goes bright white. This is because it is many times more than 1 times larger. So rather than using this into our offset here, I want to be controlling my Z height differently later on. But wait, there is a trap here. If we view our sample nodes, so our sample surface position is going to be black. If we sample our surface normal, it's going to be black. And the reason for this is because originally we were working on the assumption that this sampling UV was based on the 0 to 1 positions. However, once we have wrapped these up here, it's no longer sampling that 0 to 1 space. So I need to use, instead of this position node, I need to be using this capture of the original positions. There we go. So now if I use my viewer node again, I can see that we are capturing our positions properly and we are capturing our normals properly. This means that we can use another set position to offset afterwards, right? So this is now doing the same thing, giving us a good offset. This is our uniform one. Let's do this based on face area. So I'm going to bring this down. I'm going to just delete that briefly. So I know there's an argument in here for using the store named attributes to keep your node graph a little bit cleaner. Captures are going to be faster. So if you're interested in optimization, using the captures within the node tree is a little bit better for you. So if we take our difference, this is our ratio of face area, and I just plug this in like so, everything goes a little bit crazy because that's huge, right? So we want to be using this to scale. So multiply by our original Z value. So now we're scaling our Z value by the size that our faces have stretched, and we'll plug this in like so. Now, this looks massively too much. And the reason is because face area is squared, right? You've got two sides next to each other multiplied together. That's giving you a square for your area. So we just want to square root this divide. So let's add another math node, set this to square root, and now it's looking a lot more civilized. Just for the sake of having control, let's add another multiply on here, like so. Set this to 1, and I will plug this as well into our group input, just so that we have a little bit of extra control in case we need it. This is going to be our height multiplier. All right, so this is how you can wrap a mesh onto a UV map, essentially, right? So you can just remap any kind of flat XY existing topology into a UV map. However, what happens when there's holes? Because right now, our surface position sample and our surface normal sample, these are saying this is no longer valid because there's a hole in the mesh. And so we're just going to print 0. Basically, it's going to send you to 0. Now it's going to give us some issues. Well, this is when we might want an additional utility. So I'm going to frame these up. I'm going to pull back. There we go. Our input form and the subdivision surface that can pull back here. I will also pull back our UV map. Kind of want that to be on the outside in case you've procedurally generated your vectors there, so you don't have to store them as a vector first. So all of the rest of this, our position and normal, and then our 2 captures and the maths that goes with them and the set positions. This is all coming into one frame. Control J, F2. I'm going to rename this one to wrap mesh. And at this point, I'm also going to put all of this into a group. So Control G. And let's re-deal our inputs a little bit. So I've got my geometry, which can say is that. And we've got our mesh, which I am going to call surface. Put up to the top. We've got our source UV map. I'll leave that. And our height multiplier, I will leave that. All right. So there's another part of this which is going to be creating some kind of cutter, a Boolean cutter, or you can use it for ray casting or anything like that. The premise is, if we lay out our UV map flat, then we can extrude it to create some sort of cutter that we can use on our original flat panel here. So just to kind of give us a little bit of a circular workflow. I'm going to actually delete that group input, I don't need that. So this node group, I'm just going to name this one as the mesh wrapper. And this is going to be our output as the vase. It's not quite ready. If we have a look at our surface, and we want to lay this flat, we want to know what its UV map size and shape is. So let's grab our edge split onto here, and we will grab a set position onto here. And I'm going to plug through my source UV map into the position. Great. Once this is flat, I am going to merge by distance. So now I have one continuous surface, no holes. Once I've got this merged, I want to extrude it. So extrude mesh, and I will set this to be not individual. All right, this is pretty much it. We want to do this a little bit more intelligently because we want it to not have a hole in the bottom and also not just be a 0 up extrusion. We want this to be based on the actual size of our geometry. So I want to make sure that the volume of this is always going to be around the geometry as it comes in. So let's, first of all, let's rewind a little bit. Let's go back to our UV layout here. Let's take a geometry transform node, and we're going to be moving this down by some amount based on our geometry input. So let's take a bounding box node. I'm going to find what my minimum is, and I want to maintain this as a vector because our transform input is a vector here. So let's take our minimum, let's multiply it by 0, 0, 1. So now I've only got the Z axis active. Let's just change this to a multiply add actually. I will also subtract 0.1 from it. So we're going down 0.1. Now the reason I'm not just using the base value or multiplying the base value is in case the base value is 0. If it is 0 multiplied by anything, it's going to be 0, and then we're always going to have an intersection there. So we're just guaranteeing that we're moving it down as well. Now the top of this, the max value, this is going to be where we are extruding up to. So our extrude comes into here, and there we go. Now the problem is if we come down, our extrude follows. So rather than actually doing this on the extrude mesh, we are going to simply position the tops. So let's take a set position node. Selection is going to be the top. And I want to take my Z axis from my maximum. So let's take our maximum, separate X, Y, Z. We're going to take the Z value. We are going to add 0.1. So we're always going to be above the maximum value. And then I'm going to put this through a combine X, Y, Z. There we go. And this comes into our position. Right now, this is just stuck basically at 0. We want to make sure that we have taken our original X and Y values. So let's take our position, another separate X, Y, Z up here. And we'll just take through our X and our Y, just like so. So we're taking the Z from the bounding box, the X and the Y from our position, and just adding a little bit of a buffer space just to make sure that we're always outside that space. Just to make sure if we're doing Booleans, we don't have any awkward intersections. If we're doing ray casting, we're never going to miss a surface. This just guarantees that our cutter object exists correctly. We want to make sure that our bottom face is present. So let's go ahead as well, find our bottom face, which is our original transform node here. Let's flip that to make sure that we're pointing down. And then let's join that back with this set position, like so. and we will just merge by distance just to make sure that we have actually sealed that up. This is appearing to go quite quickly, but I will just guarantee that I'm working on boundaries. So I will use my edge neighbors and equals 1. So edge neighbors there, face count is equal to 1 into my selection. It's just going to speed things up. So this merge by distance comes into a new group output. This one is going to be called cutter. I might as well also plug through the original UV layout, just in case you ever want to view that. So I'll just connect through this noodle. This one is UV preview. And then the top one is going to be geometry, which is coming off our original setup that we did previously using the mesh wrap. So this section up here, Control J, F2, UV cutter. Let's tab back out here. Now I have a few options. We can actually use this node twice in succession to make sure that we have a working system. Because if I go straight to my geometry, you can see that we have this hole. So I want to cut out that hole. In order for us to do this, well, we have two options really. We can take our object here, our input. We can delete geometry. And we can do that based on the cutter object going through a raycast, and it is hit. So this is deleting everything on the wrong side of that. So let's make sure we're going through a not. So if we do not hit the surface, or do we not hit the cutter, then we leave a hole. You can see this is a little bit messy, but it is extremely fast. You'll see why this is important when we do the next bit, when we try this with booleans instead. So then we can just reuse our mesh wrapper over here. That is our geometry coming through. Our surface once again is the same, and our UV is the same. If I go and view this, you can see that we no longer have any of that nasty geometry that was failing. However, we have nasty geometry in a different way. So this has made a bit of a mess. The other way that we can do this is with a mesh boolean, which I kind of don't recommend because it can fail a lot, but if it does work, it will give you a much better result. So let's use an intersection between our input geometry and the cutter object. Let's have a look at what this is going to give us. So it's saying 1.2 seconds there, relatively fast for a mesh boolean and relatively accurate, in fact. If you're finding that this fails, you might need to turn on hole tolerant to deal a little bit better with non-manifold geometry. This is actually done okay, so I'm going to keep this one. Plug this into my geometry of the next mesh wrapper. Go to my geometry view. And look at this beauty. All right, so that's working nicely. You can expand upon this as much as you want. There's so many ways you can take it, and you can of course try with much more interesting geometry. For example, if I just temporarily mute these and go to my form, and perhaps we create an extrusion. How's this going to work? So let's do something like this, and let's maybe circlify that as well. Make it into a bit of a lamp. Let's delete those end faces, and maybe I'll even mark a seam around the base here. You mark seam, and I will do a seam up the bottom here. Mark seam. Now, if I go into my UV layout and I view all of this, well, it's not changed anything other than this now has a hole in it. So if I was to go into geometry nodes, and if I just re-enable, let's move this sideways just so we can see both together. If I re-enable the geometry nodes on my plane, we're going to see that we get this awful stretching, right? Because we don't have proper UVs mapped up the side. What we can do instead here is do a proper UV unwrap. So let's go into our UV editor. Let's select our object and let's tab into edit mode. This is going to be slow to update because it's doing a bunch of stuff on that other geometry. So I will just pause computation over there. So let's select everything, U, unwrap. You can see that I now get two pieces. these are kind of random shapes, right? So if I was to compute this, we're going to get weird distortions over the surface. Doesn't look too gross, but it's, you know, you get nasty meeting on the seams, and yeah, things ain't looking so hot. So what we really want to have instead is something a little bit neater. Let's go into the UV toolkit, which I recommend you downloading. Let's select one of these and gridify. Rotate -90 degrees. I'm going to go UV, constraint to image bounds, put it into here. Pivot point is to the 2D cursor, which by default is on that bottom left-hand corner. Scale, and that's just going to come into that space. Let's put this right down to the bottom. Select this other mesh. I'm going to gridify this one as well. And rotate -90. G, scale this one up. And this one as well, I'm just going to scale in the Y a little bit. This one as well, scale in the Y the rest of the way. I'm going to make sure I don't overlap these. This, in fact, I might want to fit a little bit better. There we go. So I don't necessarily want to go all the way around just because we're basically going around here. In fact, these two side pieces are going to want to be a little bit longer because these represent the verticals. So I could do something like this. There we go. So now I've messed up with my UVs. I can recompute my jar. And we can see that it's actually doing something. It looks a bit broken around the seams, but you can work out whatever treatment you want on that. But yeah, essentially we are cropping everything into our UV space and wrapping a surface to it. So this is not like a tessellate node, which is going to map one object to one face, useful in its own right. This will wrap to the UVs. I recommend you go and check out Duncan Rudd's video, linked down in the description if you want something that's more of a 3D pinning setup. He's using it for an animated armature on a vulture's wing so that he can map feathers onto the wing correctly. So much more interesting if you're doing that kind of 3D pinning thing using UV maps. In my case here, we're just using this for something like architectural facades or textured fabrics, things like that, where you want to have more of a wrap over a surface. So this is the process. Hopefully you've had fun. Hopefully you've learned something. Check the description below for helpful links and access to the files that I've made today. And I'll see you in the next one.